This is the Satellite Foundational course for GOES-R training module on derived motion winds. Past contributors to this module are listed on the front. I'm Scott Lindstrom from SIMS. Here's what you'll learn or be reminded of in this module. The important point is how the winds are created and how the heights are assigned. You'll see some examples too. Maybe you have your own examples filed away. The derived motion wind algorithm uses some, but by no means all, of the GOES-R bands. It finds traces or targets in a field of view that can be tracked for at least 3 sequential time steps. The tracers can be clouds or cloud edges, or in clear skies, they can be water vapor gradients. And the temporal frequency of the winds produced are shown. Hourly for full disk, every 15 minutes for conus, and every 5 minutes for mesos. The algorithm to compute winds uses 3 sequential scenes. Boxes within a larger box are searched forward and backward in time to estimate the vector change of targets. All of the targets are then analyzed to find the most likely, that is the dominant, motion. And a height is assigned to that vector. How is the height assigned? For clear skies with water vapor, the coldest brightness temperature in the scene is compared to GFS forecast values. For the 0.64, 3.9, and 11.2 micrometer winds that are derived, the ACHA cloud height is used. ACHA stands for the ABI Cloud Height Algorithm. If you have GO17 data, there's some extra processing done because the loop heat pipe might mean that the brightness temperatures are too warm. You can compare derived motion winds to co-located Raywindsongs, aircraft data, and model winds to compute verification statistics. This figure compares derived motion winds and radiosonde data. Overall, there is a slow speed bias at upper levels, around 200 hectopascals, because height assignments at that level are too high. There's a fast bias at mid-levels because height assignments there are too low. Wind speed biases occur because of inaccurate height assignments. Where do you find these winds and AWIPs? They're under the Satellite tab. Each of the different sectors, full disk, conus, and meso, has a tab for derived motion winds. You may or may not have all of the winds for both satellites. That depends on your own localization. Derived motion winds are loadable by pressure, that is a range of pressure, mandatory levels, which are ranges surrounding the mandatory levels, or by channels. If you find you're loading a particular variable repeatedly, of course you should make an AWIPS procedure to streamline things. I also do that to change the color of the wind barbs that are plotted. This example shows the complementary coverage provided by combining the low-level visible winds, calculated using the half-kilometer resolution band 2, 0.64 micrometer imagery, and cloud-top water vapor winds, calculated using 2-kilometer resolution band 8, 6.9 micrometer imagery. This image from July 2018 shows the remnants of Hurricane Beryl off the U.S. East Coast. Winds derived from visible data, in yellow, highlight the low-level circulation center. Winds derived from the water vapor bands, in cyan, show a trough axis just to the west of the low-level circulation center. This is a conus image with winds loaded from 4 different channels in AWIPS. The visible imagery that produced the winds over the Midwest, and the water vapor imagery, bands 8, 9, and 10, that highlight the strong jet off the U.S. East Coast. If you want to validate GFS, or some other model, forecast initializations or forecasts, derived motion wind vectors are a handy way to do that. I've changed the colors here plotted of the different bands just to help with the interpretation. Most of those upper-level winds are from band 8. Note here that the band 9 wind vector over Pennsylvania is higher in the atmosphere, 527 millibars, than the band 10 wind barb at 598 millibars. That's as you should expect, given what you know about the mid-level and the low-level water vapor channels. In this example, 15-minute CONUS sector water vapor winds help to quantify the flow within a well-defined upper tropospheric outflow channel to the northwest of Hurricane Florence. This figure shows 5-minute mesoscale domain sector water vapor winds. The vectors show a trend of improving upper tropospheric outflow in all directions as Hurricane Florence entered a phase of rapid intensification. This image from the Satellite Liaison blog shows derived motion winds in the pre-storm environment, helping to define a region of favorable wind shear in combination with the surface winds. Within that yellow circle, we have southerly winds at the surface, southwesterly winds aloft, so you know you have a region of favorable wind shear. One of the primary uses of derived motion winds is assimilation into numerical weather prediction models. Studies show that proper assimilation results in improved model forecast. A common example is the more accurate tropical cyclone path forecasts. This particular study from the UK Met Office shows that better 24-hour forecasts result as more derived motion winds are assimilated. This is a summary of what you've seen and a reminder of things to remember. The link at the bottom goes to a gozar.gov website with more information. You can also see a list of links shown in this training at the launching pad. Thanks for listening.